Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Today we are going to hopefully finish the part on views and indices, in fact, more indices than views, with two kinds of indices that we are going to look into, hash indices and B+3 indices. So we will see how wonderful they are and how so much faster they will make your queries. So these are the benefits that you will basically get from using a relational database as opposed to using Python and Pandas. So this would be incredibly fast. So before we do that, I remember that some of you had a request last week about an explanation on the exercise, on the quiz exercise on the BCNF. So I prepared a few slides for you in order to explain how this all works. All right. So in the exercise, we give you a relation R with columns A, B, C, D, E, F, and we give you functional dependencies. For the purpose of the example, I just made up some data, but you don't actually need the data in order to solve the exercises. It's just so that you see what it looks like. And in case if you are even able to do the decomposition with data inside, it's even better. But typically, just knowing the attributes and the functional dependencies is all you need to solve the exercises. But hopefully the data helps a bit. Now, who sees the dependency A functionally implies CF? Who sees it in the table, right? How do you see it? Well, for example, if you look at A when it is equal to 1, it corresponds to these three tuples right here, where A is equal to 1. Now look at C and F. It's always the same here and here. Now, the two where A equals to 2, it's always the same values of C and the same values of F. So this is how you spot this functional dependency right here. Who sees it now? All right. And now let's go for B and C. Now, B and C, let's look for twice the same. I think on purpose, I had it here. Bob and Bar here. Bob, Bar, it's the same. Now let's look at D and E for these two tuples. D is the same and E is the same, right? I think it's the only place. I could have made a table with 100 lines, but that would have been more complicated, right? But I just arranged that there is at least one example of twice the same. All right, who sees now BC functionally implies DE? All right, perfect. All right, so now the next question we are asking is this table in BCNF? Is it in the Boyce code normal form? Who thinks it is? Who thinks it is not? Okay, can somebody remind me what it means to be in the Boyce code normal form? Go ahead. Exactly, the left sides need to be all super keys, or they can be trivial, right? I could also have A functionally implies A, that we don't care about. But the non-trivial dependencies, they must have a super key on the left. How do I know if it's a super key? I compute the transitive closure, right? So let's compute the transitive closures. The transitive closure of A plus is ACF, and I cannot add anything else, right? Because I would need B in order to have others. And the transitive closure of BC is BCDE, because again, I cannot add anything. I would have needed A to add something else. Who agrees with these transitive closures? Right? Okay. So here it's simple because it's basically just corresponding to the dependencies. But in general, it might be that they are a bit longer than what's in the dependency if there's more rules. All right, so you remember how to compute transitive closures, right? We did it together, and all of you got it right, right? I asked you the question on the clicker, you all got it right. So this normally, I think you know how to do. But what do we notice here? The transitive closure of A is only ACF, so we're missing B and D and E, so that's not the whole table. And the transitive closure of BC, which is the left of the second dependency, is also not the whole table. So now we have two good reasons why it's not in BCNF, not just one, but two reasons, because neither of the two functional dependencies has a super key on the left, and they are not trivial. So it's not in Boyce code normal form. So the next step is, how do we make it a Boyce code normal form? And the answer is, to make it a Boyce code normal form, we need to split and decompose the table. It's basically not in Boyce code normal form because that table has too much information, too many columns. We need to split it into several tables in such a way that if we join back these smaller tables, we get back this table right here, right? That's in order not to lose any information. It has to be equivalence, the decomposition. So what do we do in order to decompose into multiple tables? We don't do it in a random way. We have to follow some methodology. So I need to pick one of these two functional dependencies that breaks the BCNF. So I have the choice, right? I could pick ACF or I could pick BCDE, right? Let me pick BCDE because that's the one that solves the exercises. I'll also show you ACF later, but let's pick BCDE in order to do the decomposition. Remember, the decomposition is not unique. You might have different ways of doing it. It depends on the path that you follow to decompose, right? So there's not a unique solution. But in the exercise, only one of them was actually a solution among the answers that we showed you. All right, so let's take BCDE. Who can tell me which tables I'm going to get if I decompose it using this functional dependency right here? What's the first table that I'm going to get, the columns of it? Yes? So it will have A and F, something else than A and F, and BC. So you basically have the columns that are not in here, plus those on the left, gives you a table. What about the other table, the second table? Do you know it? Somebody else? Yes, go ahead. No, somebody else? Go ahead. BCDE, exactly. So this is it. So the way I know is that I basically take the whole transitive closure, and that gives me the columns BCDE, right? You see from the functional dependency, it's basically left and right, the two sides together. That gives me one of the two tables, okay? So that gives me BCDE. Now, because of course I picked the functional dependencies so that it's not a super key, BCDE is not the whole table. There's A and F that are missing, right? So I also need to put A and F, but in the other table. But in that other table, I don't need just A and F. I also need to include the left BC, right? So this is what I get. Who agrees with this? Raise your hand. Okay. Everybody? Awesome. You have a question? B on the right? Ah, I get, yes. So this is because I chose to use the second one. I could have used the first one. Now, just close your eyes for a few seconds. Here. So if we do it your way, picking this one, we get this, ACF, and then A and the other columns, A, B, D, E. Right? Does it make sense? Mm-hmm. Yeah. So the idea is that these two tables that we get from the decomposition, we have to join them back together to obtain the initial table. In order to join them, we need them to overlap slightly, right? So that a natural join can occur. So in that case, we are going to join them on A, right? And the idea is that if you imagine that you're joining, let's start with this table right here, and we are joining it with that one. It basically means we are going to add C and F right here, taken from this table. Oh, I forgot to eliminate the duplicates. I should have eliminated the duplicates here. But anyway, there should be only 3 values. So basically, for the 1, you add foo and 12. For the 2s, you add bar and 23. And for the 3, you add 34 if you join back. But do you see you get exactly the original table if you do this, right? And the reason you do is that that table here, since we have A functionally determines CF, A basically automatically gives us a unique C and a unique F. That is the reason why we can just add them back from here and reconstruct the table, right? This is how it works. So this is the reason why what is on the left of the functional dependency that breaks Boy's code, you must have it on the 2 sides, because this is what allows you to do your join, right? It's like a pivot, some way of pivoting A, BDE, A, CF. Okay, does it make sense? Yeah. And here, if I go back now to this, what I have now in the functional dependency was BC on the left, so I need BC here, and I need BC here too, right? And now, since I have BC that gives me D and E, when I join that back, I have this. I add back D and E, but I take them from there, right? If I have Alice and Foo, that's going to give me alpha and beta. If I have Bob and Foo, that's going to give me sigma and beta. But you see, that's what I get back here. So who sees that if I join this back with this, I get this? Who sees that? Raise your hand. Okay, awesome. So this is really the idea. If I had done the decomposition otherwise without picking a functional dependency, the join would not have given me back the original table, right? It is absolutely important that you do use that functional dependency with the whole transitive closure. In this way, for one table, it's the whole transitive closure. The other table is what's on the left plus the rest, A and F. Okay. So far, so good. Who is following? Okay. So what's the next step? So we need to see what happens next. We need to now project the functional dependencies that we have on the new tables. So BC functionally determines DE nicely applies to the one on the left, right? So this one I have. And A gives me CF nicely applies to the one on the right. Okay, so I managed to preserve these functional dependencies. I still have them in this case. Now, is the table on the left in Boyce code normal form? Yes, it is, because look at this functional dependency. It's BC is a super key here because the transitive closure is BCDE. That's the whole table on the left. So now I'm in Boyce code normal form. So on the left, we're good. We're done. That's it, right? Boyce code normal form. But on the right, however, we are not done. Who sees that A here is not a super key, right? Because A, the transitive closure, it's only ACF, so CF, so I have B that is kind of too much, right? So now it means that I have still a bit of work to do on the table on the right. I need to decompose it, and the way it's done is exactly in the same way. It's just recursive. So now, what are the two tables I'm going to get from the right tables? What's the first table? Yes? ACF, exactly. So everything that is in the functional dependency, so the whole transitive closure of A, ACF. What about the other table? AB, exactly. So A, again, because that's the part on the left, plus everything else gives me this. So now, the table on the right, now I decompose it into two tables, ACF and AB. Who sees that? And now I eliminated the duplicates. You see, here I didn't do the mistake. So I really have only 3 values left in ACF. Who sees that if I join back these two tables on the top, if I join them back, then I get the table in the bottom right? Who sees that? It's a natural join on A. Raise your hand if you see it. Okay, wonderful. And the reason it does is that I was careful in the way I decompose because I used that functional dependency, ACF, that breaks Boyce code normal form. Because it breaks Boyce code normal form, it means that there will be attributes left out, and I just put them in the other table together with A. This gives me the 3 tables here. Now I preserved ACF, BCD, so now I'm good. So now actually this is beautiful because here I even preserved all of the functional dependencies. They're still there, I didn't lose anything. And just to show you an example, so at the bottom, this is the original table. On the top, these are the 3 decomposed tables. Now you see how if I take an example tuple from the original table at the bottom, 2 Bob bar beta gamma 23, do you see that it's obtained from the 3 tuples above, right? That's the idea of the join. Every time you have a tuple in the original table, it's going to project like this to the 3 tables. And if you join it back, then you obtain back the original tuple. And vice versa, if you take any tuple in the join, meaning that you would have the 3 tuples above, it has to exist as on a single row in the original table, and that's because of the functional dependencies, right? Because if you have Bob bar beta gamma, that implies beta gamma, and that would be joined with 2 bar 23 and 2 Bob and so on, right? So that would be the Chase algorithm. I didn't use the Chase algorithm here, but you could, as an exercise, you could use the Chase algorithm with these functional dependencies and prove that if a tuple is in the join, then it must be in the original table, right? Yes? Why do we need it? Because if we don't have it, we don't even have the column B anymore. See what I mean? We would lose column B. if you drop it, we would have ACF, B and E, and that's it. Sorry, D and E. Yeah. So it's just because we need to have all columns, right? Otherwise, you'd be deleting data. Okay. So that's it. And now I'm coming back. So again, showing what I did. So you're absolutely correct that I could have done ACF instead. It was just an arbitrary decision. So what if I had at the beginning used ACF instead of BCDE? Or I put my red cross just above the E. That was not on purpose. So if we did it with ACF, we would get ACF and then A plus the rest, BDE. But now, look what happened in that case. ACF I would preserve. BCDE, we lose it. BCDE is lost now because B is on one side and C is on the other side. So this is an example of decomposition where you don't lose any data. If you join that back, you get the original table. So there is no loss of data. This is in Boyce code normal form now, it's just because we lost the other functional dependency. However, we lost functional dependencies, right? So you see that depending on the way you decompose, in one case, you lose a functional dependency and you have to live with it. In the other case, you don't, right? So it's worth looking at all the possibilities. I warned you, right? In general, you cannot have all three. In general, there is no algorithm that guarantees you that it's going to be in BCNF, you don't lose any data, and you don't lose any functional dependency. That doesn't exist. You cannot have all three. Yes, you had a question? Okay, awesome. Yeah. All right. And so what some people do, because they don't want to lose the functional dependencies, instead of the decomposing into the Boyce code normal form, they decompose into another normal form, like the third one, instead of Boyce code. But you don't need to worry about that because the third one is not in scope for the exam or for this course, and the second one is also not. I just briefly showed them on a slide. You only need to know the first normal form and the Boyce code normal form, and how to turn tables that are not in the normal form to force them to be in the normal form you want by decomposing, in the case of BCNF, or by duplicating rows in the case of the first normal form. Okay, good. That's it. Any more questions? Who understands now? Who could solve a similar exercise on other examples? Okay, wonderful. Good. So that helps you doing good schema design, basically, when you have a database. And the lesson from here is that if you design a web shop, you really need to be careful to have a table for your customers, another table for your products, another table for your inventory, and so on, right? This is the lesson here. Okay, so now I can proceed back to the indices, which is what we started last week. So remember that an index, in essence, is what you had at the end of the books, where you have this alphabetical list of words that directly point to the pages that they are on. And in essence, we do the same with the relational database. We kind of build that extra page with the alphabetical terms together with the pages, except that it's not going to be a human that is going to look up the index, it's going to be a computer. So we cannot just build a page as a PDF, we have to build an actual structure in the memory of the computer. And that actual structure kind of looks like this, or could look like this, like a tree. We call it a tree because of this. It's like you've already known genealogical trees, right? Where you have all your family. So it's a little bit the same kind of trees here that computer scientists love. And so we need to build a structure like that so that the computer or PostgreSQL can very rapidly look up values. And in that case, the complexity was logarithmic because instead of looking at all the data in the table, I only looked at 4 of them. These are the ones that are marked in color. And with the others, we didn't even look at because they were elsewhere in the tree. So you see, this is an improvement compared to scanning the whole data. That's faster. And remember, the other index, the hash index, was even faster than that because that was instance. All right, so we have just built an index, and now I'm just going to expand on that and show you more details on that. So let's build an index, in fact, together. So I'm going to take this example. This is a small table. In practice, of course, you're going to have a table with thousands or millions, maybe even a billion records. So you can imagine the time it would take to scan everything. So how do we take a table with 1 billion records and make it so that you can retrieve any record based on the primary key instantly, just snapping your fingers in 2 milliseconds it's here? How do we do that? It looks like magic, but hopefully after I show you that, it's not going to be magic anymore. All right, so here I just have 6 rows so that it fits on the slides. So when we build the index, we basically need to go row by row. So when the database builds the index, it's going to take a while. So you basically write a command asking PostgreSQL to build an index. Then maybe for 1 hour or so, it's going to be slower or completely blocked because it's building the index. So what we do is this. I'm going to explain what happened here. So obviously, the index is an additional structure, right? Just like the index in your book is additional pages at the end. So we need some additional structure than the table. That additional structure, to oversimplify things, is going to look a bit like a small table, but it's not really a relational table. It's something different, but with 2 columns. I have the value and then pointers to the records corresponding to that value. So I'm going to put in there value 20 because I'm building an index on the century. I want to be able to efficiently retrieve by century. If I give you 20, then I want to have Einstein, Mirzakhani entering, for example. If I give you 19, then I want Ramanujan. So it means that I will have 20 here that points to the records with 20. So far, I've only built it for Einstein, so it points to Einstein, and then the rest will follow. All right. Now I still have to explain to you why I put the 20 in here on that first row and not somewhere else. And the magic of what happened here. There is this function h. So there is a function h that I use. It's called the hash function. And it's given to me. And I put 20 in there and it tells me 0. You know that computer scientists, they start counting with 0. They love starting to count with 0. So basically to them, position 0 is here, position 1 is here, position 2 is there, and so on. And h, which is this hash function, if I put 20 in there, gives me back 0. So that tells me I should put 20 right here and then add a record to Einstein, Switzerland. Now, what is this function h? It's called the hash function. It actually comes from cryptography. Who heard of hash functions already? Some of you? Great. So hash functions come from cryptography. You can see that as some sort of smoothie machine or mixer in which you put all the fruits, you press a button, and it just squeezes everything to some juice, right? This is what the hash function is. So here you just put 20, and the smoothie you get out of that is 0, right? It just outputs a position in the array, right? Now, this hash function, it has some desirable properties that cryptographers actually kind of like. One of the properties of the hash function is that it kind of looks random. It means that the values I'm going to get out of it are a bit random, just like the smoothie coming out of your machine, right? It's thermodynamically at least. So it's going to kind of spread my index or spread my values all over that structure. The second property that hash functions have is that they are very hard to inverse, meaning that if I put 20 in there, it gives me 0 very quickly, instantly. But if I do the opposite, if I say, okay, I would like a value such that h gives me 0, this is very hard to do, very, very difficult to do. So hash functions are designed in such a way that it only goes one way and the other way is computationally intractable, very, very difficult. In fact, that's how the blockchain and Bitcoin works, right? Because what you need to do in order to get your, I think now it's, is it 625? I think it's 625 now. So if you want your 625 Bitcoins, what you in fact need to do is to inverse a hash function. And that's the reason why it takes trillions of trials to do that. And somebody succeeds somewhere in the world every 10 minutes. What they did is invert a hash function. That's how hard it is to invert a hash function. But in the other direction, computing it is easy. In fact, if we look what's inside of h, you're going to be disappointed because what's inside of h is just typically a bunch of addition, multiplication, and modulo, that kind of things. but the modulo and the multiplication is chosen in such a way that it's hard to basically do it the other way around. For whom does that make sense? Right? Okay. And a third property of hash functions is that if we chose them well, they rarely collide. Collide means you have two inputs that give you the same value. Imagine something else that would also give me 0. A good hash function would avoid that, right? It's rare that you have two values at the same place. In that case, it just means that we would only have at each position at most one value, right? It's no big deal if it collides, but it's just going to be a bit slower, that's all. Okay, so now that I have seen that, what do? I just continue. Mariam Mirzakhani, 20, also there. So 20 gives me 0, so I know it's there. Ramanujan, 19. 19 gives me 4. Why 4? I have no idea. It's just what came from the plus multiplication in modulo, but it kind of spreads them all over the place. So now I get 4. Remember, we count starting at 0, so 4 is actually the 5th position. So I put it in there together with a pointer. Now I have -4, I put it in the smoothie machine and I get back a 3, so that goes in there. Then Pythagoras -6, I get a 1 out of that. And then 20 goes there again. Who understands? Okay, the hash function is given. Well, I give it to you. There are people who are very good at making good hash functions, by the way. So they know exactly what kind, typically when you take prime numbers, that's kind of the intuition. If you use prime numbers, that usually tends to spread them all over the place. If you don't have a prime number, it's going to collide more easily. That's the idea. All right, but of course, the content of H, you don't have to worry about that. That's completely outside of the scope of that lecture. So you can just take H as something magic that I give you, and that just instantly tells you a position from any value. Okay. Now, imagine that I get that query. How do I process that query without scanning the whole table? Can anybody figure that out? Yes, go ahead. H of 19, what that gives me 4, and that's instant. Instantly I get 4. And it turns out that a computer can also instantly access a position in a table like that, knowing the position. That's also something you do instantly. The reason why it's instant is that the size of every row is always the same. So it knows exactly at what position in the memory this 4th value is going to be. So this is also instant. And then I follow the pointer and get back Ramanujan. The magic of that is that it happened instantly because H was instant, looking at the position was instant, following the pointer was instant. So even if I had had a billion values in that table, I would still have immediately found Ramanujan in that way. For whom does that make sense? Everybody? Does that make sense? Okay, so this is the magic of hash indices. There is an extra cost, of course. It's a cost in space because you need to actually build that. You need space in your memory on your hard drive to build the extra structure that we added on the left. It has a cost. And it has a cost in time because building that takes time, right? If you ask PostgreSQL to build it, it might take 1 or 2 hours until it's built, right? And there is a third cost, which is that whenever you update the table on the right, you add a record, you modify a value. Imagine you modify a century. You change, I don't know, Mirzakhani from 20 to 21. If you change that, you need to update the index. So you see that it means the update will be slightly slower because you not only need to apply the update, you also need to slightly update the index as well, right? So an index slightly slows down when you update a table, but the benefit you get is instant answers when you have queries like that. Yes? Mm-hmm. Yep. So this would be a great idea. So you could indeed build a table like that, and instead of H, you just assign, I don't know, if you consider modern human history, then let's say we take it since we settled, so maybe that's 100 centuries ago, let's say. So 100 century, that gives us a table with 100 rows. And for every century, we put ourselves in a row, right? Sequentially. You could do this. However, you would only have solved that for the specific case of centuries like that. If I give you another table with another column to index, imagine it's a name to index. I'm indexing now on the name. Then you can no longer do that so easily because there are so many names and you also don't know in advance which names are going to arrive, right? So you might have your list of names, but then you have a new name that arrives in between. You need to add, to insert a row, but that's not efficient anymore. That's not efficient anymore. Do you see what I mean? So this is the reason why in some cases you would manage to over-optimize by just picking positions like that because centuries are highly predictable. We know exactly what kind of values we're going to get, but this is not true in general. If you're indexing names, strings, date times, doubles, maybe you want to index on doubles. So this is impossible. And then the hash function solves the issue by just creating a smoothie position out of that and putting that in some table, right? Okay. Any other questions? All right. Now, hash indices are very nice because, again, they give you instant results. So it looks like total magic, but they have limitations. A first limitation is they do not support range queries. They can answer a query such as what are the records for exactly the 19th century. But if I give you a query, anybody between the 14th and the 18th century, how do I answer that? I can't because I don't have intervals in there, right? I'm only mapping single values. So I could iterate, say, okay, I'm looking for 14, for 15, for 16, for 17, and for 18, right? But it works because these are integers. If you have strings, an interval in the dictionary, there's no way you can go through every word in the dictionary, right? And even if you would, it's not guaranteed that what you're looking for would be in the dictionary, right? So you see that for ranges, if we have a query that would typically be a select from where century between 14 and 18, then the range in the hash index doesn't help us anymore. Who sees that? Right? It only helps for where with an equality, with an exact value. I didn't see raised hands. Who understands that? Right? Awesome. So it doesn't support range queries. Range queries is just the name we give when the where clause has an interval, like a value must be higher than some value and lower than some other value. Then another problem is that hash functions are not perfect in real life. I told you that ideally they have no collisions and so on, but in practice there will be collisions. So it's not going to be as instant as I'm telling you. It might sometimes be a bit slower. So it's not perfect. And the other thing is that if you want it to be as perfect as possible, then you need a lot of space. The more space you have, the more rows you have in that structure on the left. You could create 1 trillion rows, or maybe not 1 trillion, but let's say 1 million or 1 billion rows. Then you would have very few collisions, right? It's very natural that the more space you have, the less collisions you're going to have, right? So this is very consuming in space. You need a lot of space in memory on the hard drive. And that also means you cannot build so many of these indices because that takes a lot of space. So there is another way to build an index that I'm going to show you now. That's called a B+ tree. It's a tree structure. Trees look like this. You've already seen one, actually. I've showed you one earlier. So a tree in computer science is one of the many ways you can build data structures, right? It's one of the things we teach in theoretical computer science. Trees are incredibly useful. They allow you to sort data, they allow you to look up data, and so on and so on and so on. So they have a lot of very nice properties. In fact, we can study trees for a whole semester of courses, right? So obviously, I'm not going to give you the whole theory of trees, but it basically looks like that. So the idea of a tree in computer science is that we have some roots at the top, right? So the little rectangle that you see at the top is called the root. And this is called the node, right? And this node has children, meaning its edges, arrows that point to other nodes, right? And then again, these nodes again have children, right? The children here don't have any children. The nodes here, they are called leaves, right? It's kind of very poetic, right? We have a tree and then there's the leaves of the tree, right? So inverted, the tree, by the way. The trunk would be here and the leaves would be there. But these are called the leaves, right? And this is what gives us a tree. And we can organize our data in this way. The root doesn't have any parents, right? This is the one that is over there. Now, do we have mathematicians? Okay, we don't have mathematicians. Okay, so a mathematician might object that the tree has a root, because in fact, purely mathematically, if you consider a tree is just some undirected graph with no cycles. So technically, the root is not defined. But in computer science, when you actually build our trees in memory, there is some root somewhere where it starts. And that's why we computer scientists have a root of the tree. Which is more poetic, because in nature, the trees actually do have a root, right? Okay. Anyway, in that case, I can also specify more things like how many children do I want every node to have. In that case, it's 2, right? It's called a binary tree for this reason, that every tree has 2 children, except of course the leaves that don't have any. So this is called the binary tree. But now you might ask, okay, how is that even useful, right? How is that useful? So I'm going to tell you, let me just skip that, I'll come back to this. Yeah, so it's useful because of what you can put in that tree. One of the things that you can do with trees is put, let's start with numbers. Let's put numbers in there. So here I have put in every node some number. It's a typical thing we do in computer science. Do you notice anything on the way these numbers are put in this tree? It's not random. There is some pattern in here. Do you see it? Yes? Yes? Yes, exactly. So basically, if you take 4, on the left, it's all smaller than 4. And on the right, it's all larger than 4. Right? So it's special. What it allows me to do is that if I'm looking for a specific number, I start right here. Imagine I'm looking for 3. I'm going to start here. I compare 3 with 4. 3 is smaller, right? So I know I will go on the left. And then I compare again with 2, because again, the same applies here, right? 1 is smaller, 3 is larger. So I compare 3 with 2. It's larger than 2. So I go on the right, and oh, I found it. So you see that if I insert any number right there, I can just percolate down the tree all the way to a leaf and find it without even looking at the rest of the tree. That I did not even look at, right? I only had 3 comparisons in order, no, 2 comparisons, 3 if you add the final one that checks, but yeah, 3 comparisons. That's logarithmic. The idea is that the number of comparisons, the comparisons you need is logarithmic in the size of the tree, right? So if there are 1,000 nodes in my tree, I will need 10 comparisons, right? Roughly 10 to the power of 10 is 1,000. If I have 1,000,000 nodes in my tree, I need 20 comparisons, right? 1,000,000 is roughly 2 to the power of 20. So if I have 1,000,000 nodes, I'm only going to have 20 nodes on the path. 20 compared to 1,000,000 is ridiculous, right? That's very low. That's very low. So this is the benefit of this. We can very quickly navigate the tree and find any value we want without looking at all the values. We just look at those on the path. For whom is that clear? Okay, very good. All right, it's only one of the ways we can build trees. There's other ways, for example, called heaps. That's yet another way. But anyway, that's the one that interests us right here. Now, going back to what I wanted to show you too, some other properties that we have for trees is, for example, being balanced. In that case, that tree is balanced. Why? Because I have the same depth on both sides. I have 3 nodes on the left, 3 nodes on the right, balanced. I could, of course, create trees that are imbalanced, right? I could have had, I don't know, all the 6 nodes on the left and then nothing on the right, right? Or I could have had 4 nodes on the left and 2 on the right, 2 on the left, 4 on the right. That would be slightly imbalanced. Here it's balanced. Why is balance important? Because it makes the time to go down the tree more predictable. If the tree is well balanced, no matter what I'm looking for, I'm roughly going to go down with the same number of nodes. If my tree is imbalanced and there's a lot of nodes on one side and less on the other side, then in some cases, I'm going to need a lot of comparisons because it's very deep. And in some other cases, very few because it's not deep, right? But balance makes it more predictable, right? That brings it closer to always logarithmic, right? One way of doing that is in terms of weight. Imagine that every one of these nodes weighs 1 gram, right? And you're just like holding them and like measuring how much it weighs, right? So in that case, for example, you would say it's balanced within a certain tolerance. So for example, here I tolerate that there is a difference of 1. Here I don't tolerate it because, for example, on the left at that node, you have a weight of 5 on the left. You see 1, 2, 3, 4, 5 nodes. And then one node on the right, this is imbalanced. You have a difference, 5 minus 1 gives you 4. So here you might not accept that. You might say, no, 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 that's not okay. Please rebalance the tree back into a position that is more balanced, like this one, for example, right? And there are algorithms to reorganize the tree in that way, to just make it balanced again. Okay. This was still imbalanced, by the way. You see why it's imbalanced? It's because for the red node, you have 1 here and 3 here. So you can still reorganize a bit. Now you have 2 and 2. Now it's balanced, more or less balanced. Okay? So you don't need always the same number of children, but you want the weights to be kind of balanced. All right. So if it's balanced, it kind of looks like a pyramid, some sort of pyramid. Who is following me? Wonderful. You're doing great. You wouldn't imagine the number of hours we can spend on trees and algorithms in theoretical computer science lectures. Very, very, very complex. Okay, so we are interested in this kind of tree because it makes it very easy to look up a value. And if you think of it, what do we need? We need an index. What is an index? It's a way to look up a value efficiently. That's exactly what we need. Now I can use that in order to retrieve a value very efficiently, right? So that's the idea, because you know exactly where to go depending on what you want to compare. So I showed that to you with numbers because that's just easier, but you understand that I can also do it with words, right? If I sort them alphabetically, I can also compare words, and a word comes before or after the word in a dictionary. So I could put my nodes in there in such a way that everything that is on the left comes before the word or in the dictionary, and everything that is on the right comes after the word or in the dictionary, right? After or equal, right? I tolerate equality too. You actually notice that or is actually reappearing as a leaf on the right, right? So it's basically strictly lower, strictly before is on the left, and equal or after is on the right. Who sees that with the strings? That I can also do it with strings? Yes? Okay, I see nodding heads. So you see, it's very powerful because I can build that for anything that I can sort, anything that I can compare. I can do it with integers, with strings, with dates, anything I can compare. I can basically build a tree like that. What are these arrows that I put at the bottom? These are the pointers to the database records. Just like the hash table, remember, we point back to the records corresponding to a value. So what happens is that you're looking for a specific value. Let's say you're looking for not. That's before or. Let's go on the left. Oh, that's equal, so on the right. And there you go, you found it. And then you follow that. That brings you right to the database record in your table that you're looking for, that you can directly access, right? That's how it works, right? Just because of that magic that you have these rules over there. So I think now it's time to take a break because I see that it is 11, and then we'll continue after the break and looking at these B+ trees. I will also have an animation on how to build them. If there is time, we might even start with data cubes. I think that we are good with time. So I'll see you in 15 minutes. Thank you.